This interactive simulation in which we heat liquid water and air in a sealed container. So we start out at 25 degrees and we can set the initial volume of water, in this case 0.89 liters. The total container is 1 liter. And we start at 25 degrees, and so what I'm showing you is after we raise the temperature to 160 degrees, and what has happened is the liquid has expanded, so now instead of occupying 0.89 liters, it occupies 0.991 liters. And so the gas volume has been compressed significantly. The pressure now is much higher because that gas volume was compressed and because the saturation pressure of water is higher at 166. Now on the right side of this simulation, we're displaying the amount of oxygen and nitrogen. So initially, almost all of it is in the gas phase and a small amount is dissolved. As we raise the pressure, we increase the amount dissolved. As we raise the temperature, we decrease the amount dissolved. We're raising both, of course, as we raise the temperature in this simulation. And it shows at this condition, this relatively high pressure, a significant fraction, almost half of the oxygen, the original oxygen, is dissolved in the liquid phase. The rest is in the gas phase, and it's hard to display a gas volume with this large a liquid volume. And so this mimics the procedure used, for example, when zeolite crystals are grown from solution, where autoclave is sealed and put in oven and raised to a significant temperature to allow the chemical reactions, the synthesis, to take place. So let's look at this simulation to see the behavior of the system. So here's the simulation, and let's start by saying we have 85% of the container filled with liquid water, and then above it is air and water vapor, and we're at 1 bar and 25 degrees. So then what we do in the simulation is we raise the temperature. We observe first that the volume of the liquid is increasing because liquid water expands when heated. It's not a dramatic increase. We're up to 115 degrees, and it's increased from 85 to 90% of 1 liter. And then on the right, we show that a small fraction of the oxygen and the nitrogen are dissolved. That's the purple at the bottom in the bar graph, and the green shows the amount that is in the gas phase. So as we continue to raise the temperature, first thing to notice is the pressure now is going up rather dramatically, and this is for 2 reasons. One, the saturation pressure is significantly higher at 183 degrees, and 2, the volume of the gas is decreased from 0.15 liters to 0.037 liters. And so just from ideal gas law, the pressure of that gas is increased. Now, it hasn't increased as much as it would if there was not some of the gas dissolving. So you notice the fraction dissolved has increased because the pressure is higher in Henry's law. As I start to get now to very high pressures and very little gas volume, notice now a significant fraction of the oxygen and nitrogen are dissolved. And if I continue to raise the temperature, now we're at 45 bar pressure, very little vapor volume left, and that's part of the reason for the high pressure. And also notice almost half, or very close to half, of the oxygen is now dissolved in the water. And I could slowly increase this further, and I'll do that by holding down the Alt key while I move to the right. Notice we're at 51.6 bar pressure. Now more than half the oxygen dissolved, and it looks like about half the nitrogen is dissolved. And as I continue to increase, notice we can get to extremely high pressures. We have very little vapor volume left, and most of the gas now of the oxygen is actually dissolved. And then as I push too high, we set a pressure limit on the container, and so then the container would break. So this simulation represents behavior when a liquid's in a sealed container is used in some inorganic synthesis, such as a zeolite synthesis. And it takes account of ideal gas law, saturation pressure, expansion of liquid, and solubility of oxygen and nitrogen in water.